Hello, everyone. So just to finish out this segment regarding kinetic theory with this heat, just wanted to go through just a couple things here. Specifically, the average translational energy of um, a gas, um, or really any substance that the particles are moving in random orientation. So this is this animation here is when you pull up on Wikipedia, you get this animation, and I think the animation helps see what's going on. So if you focus your eyes on one of the red dots, you'll see that its motion is in a straight line until it comes in contact with either the wall or another moving object, uh, which is to represent the atoms. So if you think of the atoms moving around in the room at the time, at this very moment, they move in a straight line until they run into something else. And then depending on the motion of everything and the energy transfer, then it goes in another direction in a straight line until it hits another object. So this random orientation um, is related to the kinetic energy within that system, which is what we can calculate with this Ke with a bar over the top, which is the average translational kinetic energy. And that, or kinetic energy in general, is defined as 1/2 mv squared. In this case, we're talking about v squared of the RMS. That RMS is the root mean squared, and that is defined as the square root of the square of the average of the velocities of each of these particles. So a little confusing there, but again, the VRMS is the directly related to the square of the average velocity of all of the particles in the system. And we have to use this VRMS um, because of the velocity distributions of this of the particles in the system. This chart is represents the speed of the velocity distribution of the particles at different temperatures. So if we look at a gas at 300 Kelvin, um, which is this blue curve here, the most probable speed is at this 400 meters per second speed. The y-axis here is percentage of molecules, basically a number or number distribution. So you can see that there's a pretty good span of speeds of particles in the system. They're not all at 400 meters per second, um, but there is a distribution. And this VRMS, this root mean squared velocity, ends up being about 484. It's moved over towards the right here because there's a little extra tail. You'll notice it's not a strict bell curve, but there's this little extra tail here, and so that helps to kind of move things over a little bit. Um, anyway, point is that with this Maxwell distribution of velocities, then we have to use this VRMS in our average translational energy calculation. Now we can notice then that as we increase the temperature of our gas, so now we move this to 1200 Kelvin, so that's 4 times as hot, we have a broader distribution of velocities, but obviously the velocities are now broadening into the higher range. So we have higher temperature. That means that the speed of the particles, or the average speed of the particles, is greater. So we're up to now with a root mean squared velocity of 967. So twice the speed that we were at 300 Kelvin. Um, so from this chart we can see a couple of things. One, as we increase temperature, the speeds of the particles increase. Two, the VRMS obviously increases as well, um, and um, And the last part is that we have a broader distribution of velocities. But this is an important concept to know and to have. This VRMS is the square root of the square of the average, and that we use that VRMS in our average kinetic energy calculation in order to get the average translational energy of what the system that we're talking about with the Brownian motion and the kinetic energy. So don't have a specific problem for you. Just wanted to get this concept down because I had a few questions about it. So hopefully it is helpful. If you have further comments or questions, please leave that or ask it, and we can discuss and figure it out. So thanks.